Okay, so today we will be discussing problem D of code forces round 90 div2. The name of problem is more wrong. Firstly, this is an interactive problem. The problem statement says that the jury has an hidden permutation P of length n and we can ask certain queries. Each query is of form of two integers L R, basically a range. L is between 1 till n minus 1 and R is strictly greater than L and less than n. And the cost of this query is R minus L squared coins. And in the answer to this query, the jury will return the number of inversions in the subarray of permutation from L till R. And the number of coins we have is 5n squared. So within 5n squared, we have to find the maximum element in P. Okay, so let's discuss this problem. One of prerequisites for this problem is the divide and conquer technique. So you should know a bit about the divide and conquer technique. So let's start by taking an example over here. So let's start by taking example of this first permutation, that is 1 3 2 4. Now one thing to notice over here is that since this the P given to us is a permutation, so the max element will be n. So a permutation is basically an array of numbers from 1 to all the way up till n. So for example, for 4 you have 1 2 3 4, for 5 you have 1 2 3 4 5, and these can be like randomly arranged. So over here it is like 1 2 3 4 as 1 3 2 4. Now for each query, let's just understand what will be the answer for each query. So for each query, it is giving us number of inversions. Now what is an inversion? So an inversion is basically a pair of indices ij such that a of I is strictly greater than a of j and I is strictly less than j. So basically what it means is that a inversion is such a of I and a of j such that a of j is greater than a of I is greater than a of j, but it lies before a of j. In that case, it will be considered an inversion. So now let's get to how we can solve this problem. Okay. So firstly, let us consider what can be the property of the maximum. Initially, each of the n elements from, we have n elements from, let's just say, I will just name it a1 rather than p1. So from a1 till an we have n elements, each from 1 till n, and each of them can be like equally likely, each of them can be equally maximum. So means each of them has an equal probability of being a maximum. Now given two elements a of I and a of j, and let's just assume that these are not same, so there is some 0 or more elements lie in between them. How can we check which of them is greater one? So basically we want to find like the maximum in this array A, and it's a permutation, so no two elements are equal, and we have this a of I and a of j, and we need to find some way to compare this a of I and a of j. And the only query that we can ask is like L and R. So the only query that we can ask is LR, where LR will give us the number of inversions in L till R. So using this query, we want some way to compare. So using this query where LR will give us number of inversions in range from a of L to a of R. So using this, we need to find some way to compare a of I and a of j. So what we can do is that we can consider all the cases that there can be. First thing is that a of I is never equal to a of j, because this is a permutation and I is like strictly less than j. We are assuming that thing. So I is strictly less than j, so I lies somewhere over here, then j will lie somewhere ahead of I, and so a of I is not equal to a of j because a is a permutation and each element in the permutation is distinct from 1 till n. So there can be two cases. The case 1 is that a of I is strictly less than a of j, and case 2 can be like a of I is greater than a of j. Okay, so we have these two cases. Okay, so we have these two cases. So how do we determine which of the cases it is? So first, let's just consider this query. So for now, consider what will be the answer to this query. I from I till j minus 1, what will be the answer to this query? It will be number of inversions in range I till j minus 1. Now j minus 1 is like greater than equal to I, so it can happen like j is equal to I plus 1. In that case, basically I j minus 1 will equal to I, which is one element, so 0 inversions. So even such a thing can happen, but basically the query I till j minus 1 returns the number of inversions from the element I till j minus 1, so just before a of j. So this basically will return us, so this is something a of I and a of j minus 1, and over here we have a of j. Okay, and the first query will return us the number of inversions from a of j till a of j minus 1. And now let us consider one more query. So we'll make these two queries I till j. Okay, so the first query gave us answer from a of I till a of j minus 1, and the second will give us the answer from number of inversions from a of I all the way up till a of j. Now the first thing to notice is that, let's just say that n of I till j represents number of inversions in range like a of I all the way up till a of j, assuming that I is strictly less than or equal to j. One thing to notice over here is that n of I, the number of inversions in from I till j minus 1 is always less than or equal to number of inversions from I till j. Why? Well, because let's see, if you are counting an inversion in a of I till say a of j minus 1, fine, this is a of j and this is j minus 1. Remember, what is an inversion? An inversion is such an index a of for now x and a of y such that x is strictly less than y, so that a of x lies before a of y, but a of x is strictly greater than a of y. That's what an inversion is. A of x is strictly greater than a of I, but a of x lies before a of y. Okay, now what happens when an inversion is included in a of I and a of j minus 1? Well, in that case, this a of x and a of y, both of them must lie in this range a of I and a of j minus 1 from over here to here. But in that case, they will also lie in a of I till a of j, which means that every inversion that's part of this a of I till j minus 1 is also part of this a of I till j. So every inversion that is in I till j is all I till j minus 1 is also in I till j, and it may happen that a few extra inversions are added in case of a of j. So number of inversions in I till j is always greater than or equal to number of inversions in I till j minus 1. Now consider what happens when a of j is added to this I till j minus 1. How many inversions how many more inversions can there be? Basically, what the question I am asking is, what will be this difference? Okay, so the question I am asking is, what will be this difference? Now you see, in any inversion that is added after like a of j is added, so in any inversion that is present in range I till j but not present in range I till j minus 1, so in any inversions, so this is a of I, this is a of j minus 1 and this is a of j. So in any inversion that comes only after a of j is added, so it's not present in this range, but it comes only after a of j is added, then the obvious thing is that its second element is a of j, and there must be some element over here, a of, let's just say, x. Now this a of x has to be strictly greater than a of j. Okay, this a of x has to be strictly greater than a of j. Now what does this tell us is that, extremely sorry, I think I added page. Oh yeah, so what this tells us that, considering that it was case 1, that let's just say that if a of j was the maximum element in I till j, in that case there would be no x such that x is strictly less than j, and x is not like just strictly less than, but x is less than equal to greater than equal to I, and x is less than equal to j, and a of x is strictly greater than a of j. There won't be any such element. So it would mean that adding j would not lead to an increase in number of inversions, and so n from I till j minus 1 will equal to n from I till j. So that gives us a test for determining if a of j is maximum in a from I all the way up till j. How will we do that? Well, basically we just calculate n from I till j minus 1 and check if it is equal to n from I till j. If it is equal, that means that a of j is maximum element, and if it is not equal, it means that a of j is maximum elements in I till j, and if it is not equal, it means that there is some element greater than a of j which lies in this range I till j. So how can we use and also one more thing that we have to consider, what is the cost of it, because you see over here they have given us that we have in total at most 5n squared coins. So we also have to consider what will be the cost of this determining if a of j is maximum or not. Well, first is that the cost of L till R operation is like R minus L squared. So what will the total cost of this operation? Well, it will be j minus 1 minus I squared plus j minus I squared. Let's just say that length is equal to j minus I, then this whole is like less than equal to 2 into length squared. Fine. So the total cost of this operation determining whether a of j is maximum or not is 2 length squared. So now you can pretty much see how this will go ahead from over here. We will just be using divide and conquer. So how will we use divide and conquer? Well, firstly take this array that you have from a1 all the way up till a of n. You have this array. If like n is equal to 1, so the size of your array is just basically 1, then you have your answer, because in one, if you just have one element, then it is the maximum element. There is nothing else to check for it. Otherwise you are going to divide your array into two subparts, a1 all the way up till a of m and a of m plus 1 all the way up till a of n. Then you will use some algorithm to find the maximum in this first subarray. So a1 up till a of m, you assume that you have this a of l as your maximum in this subarray, and assume that you have a of r as your maximum in this subarray. So you have these two candidates, and you know that the maximum is definitely going to be one of them. So what can you do now is that you can use the algorithm that we have developed over here to check which one of them is maximum. So you basically make two queries. You make a query till L till R and check if it's equal to query from L till R minus 1, and if it is, then maximum is A of R, because A of R is maximum, otherwise A of L is maximum. So you get the point, right? We are basically using some algorithm to find that A of 1 till M maximum in this range, A of 1 till M, we have this maximum A of L, and we are using something else to find maximum in this range, A of M plus 1 till N. So when we have this element A of R and A of L, so the maximum is definitely going to be one of them, and we check the number of inversions from A of L till R minus 1, and then we check the number of inversions from A of L till R. Now if the number of inversions from A of L till R don't increase, it means that A of R is greater than every element in A of L till R. So it means that A of R is also greater than A of L, which is to say that A of R is the maximum element, because there were only these two candidates for the maximum. Now consider what will be the time complexity, basically the number of coins. Let's just say that T of n is the number of coins we require for an array of length n. So let's just say that if we want to calculate maximum for an array of length n, then we require T of n coins. Okay, so how do we calculate the, consider developing this recursive function. So for T of n, what we do, the first thing that we do is that we calculate the maximum for two subarrays, that is half of this T of n. When we calculate the maximum for these two subarrays, the next thing that we do is that we compare this A of L and A of R and check them. After we have these two maximums, we check them and see which one of them is greater. How much does this cost? We have seen over here that the cost is less than or equal to 2 into length of squared, which is 2 into n squared. Okay, so over here you can see that this basically develops into a recursive, in a sense, you can just keep on expanding this, and this would develop into something like this over here, 2 into n squared into 1 plus 1/2 plus 1/4, something like this. It won't actually develop into this thing, but something like this would be greater than or equal to this thing, which is actually 4 into n squared. So the number of coins that we'll be using is actually less than or equal to 4n squared. Of course, there are some limits or some round offs over here that we are using, so but it would be within our limit of 5n squared. So we'll be using at most 5n squared for this for an array of length n. So that would be the maximum number of coins we'll be using. Now let's just go through the code of this problem. Round890. Okay, and yeah, okay, so because this is an interactive problem, I have written two functions, query and answer. So query from L till R basically queries the system for range L till R and returns the number of inversion itself, and answer the index of max element, it will just answer itself. So yeah, because we are doing something like a binary search, I have written this function get L till R, so it would actually give us the maximum index from L till R, and we are answering get from 1 till n. Okay, so first thing, if L is equal to R, then we'll just return L. And actually I have tried to optimize what we are doing over here. So if you see, if L is L plus 1 is equal to R, that is that the elements lie side to side. In that case actually we are making a redundant query. We are querying L till L, and so in that case actually if you look at it, if L till R is actually equal to L till L plus 1, in that case we are making two queries, L till R minus 1, which is actually equal to L till L, and we know the answer for this query. It's always going to be 0. Okay, we know that when there is a single element there isn't going to be any inversion. So we know the answer for this query, so we are making a redundant query over here. So what I did was that if L plus 1 is equal to R, then we just query this L till R, and if it is equal to 0, then yes, L till R is equal to L till L, and R will be the maximum element. So A of R is greater than A of L. Only in that case L till R can have no inversions, and if it is equal to 1, in that case L will be the maximum element. So yeah, that's like a small optimization. Then we take the mid over here, and then we get the maximum element from L till mid and the maximum element from mid plus 1 till R. Again I have used this same thing, like L plus 1 is equal to R, then I have used this small optimization. In other case I have said the inversion 1 is like the number of inversions from L till R minus 1, and inversion 2 is number of inversions from L till R, and I've checked if number of inversions from L till R minus 1 is equal to L till R. If it is, then R is greater than every other element, so R is the maximum, otherwise L is the maximum. And if you just want to run this code, actually testing for the interactive problems is a bit difficult. I have written blog on how you can do so a bit more easily in Linux. So over here I would just pass in my, so actually you can see this is in some sense like a script I have written to test this problem, and I will just run my D and D checker and see. As you can see, it has this interaction, and over here you can see that it has passed all the 3 test cases that I gave it to it. So thank you for attending this thing, and yeah.